What's up, guys? New topic. We're looking at rates of reaction. This will serve as like a GCSE recap where we look at the factors that affect the rates. Before we start though, please like, subscribe, share with anyone you think will find it useful. It really helps to grow the channel. Very much appreciated if you do. Let's get into it. So, here. In order for a reaction to happen, we need three things. We need a collision. We need the collision to have at least the activation energy. So this obviously means greater than or equal to, and EA is the symbol that we give for activation energy. And last thing we need is the correct orientation. Which obviously means it needs to be reactants need to be facing in the right direction, right? So if any of those things, any one of those things doesn't happen, the reaction doesn't happen, right? So here we've got our reactants, they're colliding, but maybe it doesn't have the activation energy or it doesn't have the correct orientation. No reaction takes place at that point, okay? If, however, all three of these things happen, at that point we do get a reaction, right? So that's what happens here. Again, everything's happened. We've got our collision, new products have been formed, and again it's any one of these. If any one of these doesn't happen, we're in trouble. Now let's look into the factors. So we take this first one. Hopefully you can see this is talking about concentration, right? We've got particles that are dissolved in what's supposed to be water, right? So this is an aqueous sample. And clearly, hopefully you can see that we've got an increase in concentration, all right? Worth us knowing that concentration is basically the number of particles per unit volume. Hopefully you can see here we've got a low concentration and here we've got a higher concentration. And then let's think about these factors. Now whenever we're describing this, so here we're talking about moving from a low concentration to a high concentration. Wherever we're explaining the factors that affect rates, we think about it in these 4 steps. Sorry, let me get these two the other way around. So we think about the factor, the particles, so what effect the factor has had on those particles, the collisions, and there we think about 2 things within that. We think about the number of collisions and the force of those collisions. And then we think about what effects that has had on the rates. Okay, so if we're taking our concentration again, factor, so we've increased the concentration. Particles, more particles. Per unit volume. Let's say per dm cubed in this case. And therefore, more collisions, right? The particles are closer together. There are more of them, and so there are going to be more collisions. So more collisions. And therefore rates, faster rates. So if we talk about all of these things, the factors, the particles, the collisions, the rates, we're likely to get all marks that we could need when it comes to talking about factors affecting rate of reaction. Yeah, so let's move on to the next one. So here is something that's very similar, right? We've got, this time they're not dissolved in water, these are gas molecules. So here we're talking about pressure. And again, pressure as a similar thing to concentration. Here again, we're talking about the number of particles per unit volume, right? So here we've got a low pressure. And here we've got a higher pressure. And I've done this for a reason, right? So we've got one where we've got more particles within the same container, the same volume. And in the next one, we've literally just lowered the volume. And here, I hope you can see, in both cases, the particles are closer together. There are going to be more collisions. So these are the sort of two ways that we can increase the pressure, by adding the number of particles and by decreasing the size of the container. And that links back to PV equals nRT, if you remember, right? So pressure, volume, moles, rate constant and temperature. Yeah, so it links back to that, and I'll put a link up here to remind you of that ideal gas constant stuff. So again, let me move this across. We've got a bit more space to write stuff here. So moving from the low pressure to the high pressure, we've got an increase in temperature, in pressure, sorry. When we think about the particles, more particles per unit volume. Let's say dm cubed again. Collisions, more collisions. So faster rates. Important to note, like, neither of these factors are having any impact on the force of these collisions. The collisions are still happening at the same force, but there are more collisions, right? Next, hopefully you can see here, difficult to sort of visualize, but this is showing us the particles are moving faster, and that's because we've got an increase in temperature, right? So we've got a low temperature here and a higher temperature here. So again, let's think about those four things. So our factor, we've got an increase in temperature. And at that point, the particles have more kinetic energy. In essence, that means that they're moving faster, right? So because of that, we're going to have more collisions. With greater force. More collisions with greater force. So again, this is going to mean more particles, therefore, more particles have at least the activation energy, therefore faster rate. And worth mentioning here, because both of these things are affected in terms of collisions when we increase the temperature. If we doubled the temperature, the rate would be much more than doubled, because both of these things are increasing, both the number of collisions and the force of those collisions. Next, here we think about this blue being a solid, right? These blue bits being a solid. So what we've got here is, say, a big solid rock, and we say that this has got a low surface area. And essentially what that means is that we've got some particles that are sort of held inside others, right? So what's going to have to happen here is that as these reactant particles start to react, they're going to have to react with the outside ones first before they can access the inside ones. And what's happened on the right hand side is this larger solid particle has been broken up into smaller ones, right? We've got the same number of particles total, but they've been broken up into smaller pieces. So here we've got a higher surface area. And I hope that you can see that in this case, none of the particles are obscured by any others, right? So here, let me explain over this side. Here we've got an increase in surface area. When we talk about the particles, we can say there are more exposed particles. So because of that, we're going to have more collisions. And because of that, we're going to have a faster rate. And again, like often we're asked about if we grind something up into a powder, what effect's that going to have on the rates? Sometimes we don't make that link between the facts that we've got smaller particles of solids, therefore a higher surface area, right? But we do need to be able to make that distinction. Last one. So here, our purple line represents no catalyst. And our red dash line represents when we do have a catalyst. And I'll just label the segments of this. So here we've got our reactants. At the end we've got our product. And we've got two different numbers for our activation energy, right? So here, the peak, the gap between these two, this is our activation energy with catalyst. And I'll do it in a different colour. No. More word. Nice. And this represents our activation and energy without catalyst. So the point here is that what happens is that once we add a catalyst, our activation energy is lowered. So if we come back here, even if we have the same number of collisions, now we've got a lower activation energy. It means more of these collisions are going to result in a reaction, right? So, factor, we have added a catalyst. Which decreases activation energy. Therefore, more collisions have at least the activation energy. Therefore, faster rates. Important to note, we haven't got more collisions. We've got the same number of collisions, but more of these have at least the activation energy, right? So, we've got 4 questions actually that I want you to give a go. And what I'll do is I'll answer them at the end of the next video. So give it a screenshot give it a go, I'll answer it then. Now on to what we did last time. So here, remember, we're looking to identify the charge of everything. Sodium here, +1, oxygen -2, the hydrogen +1, oxygen -2. And again, same here, -2, +1. You can see here, nothing has changed oxidation number. So it's neither redox or disproportionation, right? Next, here, the oxygen is -2. We've got 2 lots of those, so the sulfur is +4. Oxygen's in its elemental state here, so it's 0. On the right hand side, again, the oxygen will be -2, and the sulfur will therefore be +6. Hopefully we can see stuff going on here. So we've got a change here, and we've got a change here. Perfect. So moving between these two, we've gone from S4 plus to S6 plus 2E minus in order for that to happen. And for here, we've gone from O2. We'll keep it simple, or we'll go half O2 to O2 minus to E minus. So here we've gained electrons, reduction. We can also say it's an oxidizing agent. Here we've lost electrons, oxidation. We can also call it a reducing agent. So yes, no. Last one. This is a nice exception actually. Here, hydrogen is +1 and oxygen -1. Very strange one. It's the only exception for oxygen really that you'll come across. Oxygen here is -2 and hydrogen +1, back to normal, and 0 here. So hydrogen doesn't change, but hopefully you can see here that oxygen has done 2 things, right? So we've gone from, let's go, so let's say half O2, or not even half O2, my apologies. We've gone from O -1 to O2 minus, therefore we have gained an electron, right? So that's reduction, but also we've gone from the same place. We've gone from O minus to O2. Let's call it half O2 for simplicity, and we'll have gained an electron there. So there, redox has happened, and it's our special type of redox. It's disproportionation. Hope that helps. Good luck with the previous set of questions. I'll see you next time. We'll continue rates of reaction. Happy revising.